all to today's class. So in this class, we are going to discuss about wave motion. Before going on to our topic, let me ask you a question. Have you ever tried to throw a stone into water? I think you all might have done this in your childhood, isn't it? What happens then? What do you observe? Yes, as you can see in this video, when a stone is dropped into water, a disturbance is produced. And this disturbance is spreading from its origin to other places. So this is an example of wave motion. So we can simply say that wave motion is the propagation of disturbance produced in one part of the medium to the other parts by the vibration of its particles. Also, wave motion is a means of energy transfer. That is, the energy received by one particle is transferred from particle to particle, thus spreading all over. Now, can you list out some examples of wave motion? Radio waves, sound waves, light waves, all these are examples of wave motion. You can find more examples and can note down in your science diary. Now, let me ask you another question. Do all waves need a medium for their propagation? The answer is no. Not all waves need a medium for their propagation. Waves which need a medium for their propagation are known as mechanical waves. For example, sound waves, water waves, these are examples of mechanical waves. On the other hand, electromagnetic waves such as radio waves, light waves, etc. do not require a medium for their propagation. They can travel through vacuum. What is vacuum? An empty space. So in this video, we are focusing more on mechanical waves. Mechanical waves are mainly of two types. Do you know what are they? Transverse wave and longitudinal wave. To know more about transverse wave, let's see an activity. Here, one end of the rope is fixed and a ribbon is tied onto it so that the ribbon can clearly be seen. Now, the other end of the rope is moved up and down. What do you observe? A wave is formed, isn't it? Now, look at the motion of the ribbon carefully. As the wave is formed on the rope, the ribbon is moving up and down, but its position on the rope does not change. That is, the ribbon is vibrating in a direction perpendicular to the direction of propagation of wave. So here the ribbon represents each particle on the wave. So we can simply say that a transverse wave is a wave in which particles vibrate in a direction perpendicular to the direction of propagation of wave. Now let's see some of the examples of transverse wave. Water waves, light waves and all other electromagnetic waves such as radio waves, X-rays are transverse. Also, waves formed on a string or rope, these are all transverse waves. In case of water waves that we have seen in the beginning of our video, the water particles move up and down while the wave moves outward. When we consider light waves, what happens? The electric and magnetic field oscillate perpendicular to the direction of propagation of wave. And when we consider the waves formed on a rope that we have just seen, the particles move up and down perpendicular to the direction of propagation of wave. So I hope transverse wave is clear for you. Before moving on to the longitudinal waves, let's discuss the characteristics of a wave. What are the characteristics of a wave? Amplitude, wavelength, period, frequency, speed of a wave. These are the characteristics of a wave. We will discuss them one by one. First, amplitude. What is amplitude? Amplitude is the maximum displacement of a particle from its mean position. What do you mean by this mean position? It is the resting position of the particle. So we can say that amplitude is the maximum displacement of a particle from its resting position. It is denoted by small letter a. Now let's move on to wavelength. Wavelength is the distance traveled by the wave by the time a particle completes one vibration. Now, what do you mean by one complete vibration? It means the particles start from its resting position, move towards the maximum in one direction, then to the maximum in the opposite direction and come back to its resting position. It is termed as one complete vibration. Or simply we can say that the particle moves up, down and back to its starting point. So, the wavelength is the distance traveled by the wave by the time a particle completes one vibration. Now, we can also say that wavelength is equal to the distance between two consecutive crusts or two consecutive troughs. Crust is the highest point and trough is the lowest point in a transverse wave. Wavelength is denoted by the symbol lambda. It's a Greek letter lambda and its unit is meter. Next is period. What is period? Period is the time taken for a particle in a medium to complete one vibration. So we have seen that wavelength was the distance taken by the particle to complete one vibration. At the same time, what is period? Period is the time taken for the particle to complete one vibration. It is denoted by capital letter T and its unit is second. Next is the frequency. Frequency is the number of vibrations made by the particle in 1 second and it is denoted by small letter f. Frequency and period are related as f is equal to 1 by t. Now, is there any relationship between frequency f and wavelength lambda? Yes, both are inversely proportional. That means, as you can see in this picture, when frequency increases, what happens to wavelength? Wavelength decreases and vice versa. Next is speed of a wave. Speed of a wave is the distance traveled by the wave in 1 second. It can be written as speed is equal to wavelength lambda divided by period t. Since 1 by t is equal to frequency f, we can rewrite this equation as speed is equal to frequency f into wavelength lambda. And its unit is meter per second. So that's all about the characteristics of a wave. Now let's move on to the longitudinal wave. Longitudinal wave is a wave in which the particles of the medium vibrate in a direction parallel to the direction of propagation of wave. But in case of transverse wave, what we have seen, the particles vibrate in a direction perpendicular to the direction of propagation of wave. But in this case, it is parallel. Note down that difference. And this creates compressions and rarefactions alternatively in the medium. Now let's look what compressions and rarefactions are. Compressions are regions in a longitudinal wave in which the particles are closely packed. It represents areas of high pressure. And rarefactions are regions where the particles are spread apart. It represents areas of low pressure. The compression is denoted as C and rarefactions are denoted as R in this picture. Now let's see some of the examples of longitudinal wave. First is the sound waves. When we speak, sound travels through air as longitudinal waves by compressing and expanding the air molecules. Next is the waves produced by the vibration of a tuning fork. You all might have seen a tuning fork in your science lab. What happens when you strike a tuning fork? It starts vibrating, isn't it? So when a tuning fork vibrates, it pushes and pulls the air particles around it. This creates compressions and rarefactions that move parallel to the direction of sound wave. Next is the waves produced in a spring. If you push and pull one end of a stretched spring, you create a longitudinal wave. So these were the examples of longitudinal waves. So we have studied about transverse wave as well as longitudinal waves in detail. I hope it's clear for you. Now let's move on to sound waves. We know that sound travels through various media before reaching our ear. Which are those medias? Find out by yourself. Now, do you think whether the speed of sound will be same in all these different medias? No, the speed will be different. It depends on the temperature of the medium. As the temperature of the medium rises, what happens to the speed of the sound? It also increases. For example, speed of sound in air is 331 meter per second at 0 degrees Celsius, but rises to 343 meter per second at 20 degrees Celsius. Alright, now there is a question for you. We all know that light waves get reflected when it hits a smooth surface. What about sound waves? Do sound waves also get reflected? Let's see this with an example of an activity. Now look at this picture. Two pipes A and B, a smooth surface and a stopwatch are arranged as shown in the picture. The sound waves pass through the pipe A, gets reflected when it hits the smooth surface and can be heard from pipe B. What do you understand from this activity? Yes, sound waves also get reflected from smooth surfaces, just like light waves. Is that clear for you? Now look at this picture. What do you observe in this picture? You can see that the sound produced by the girl is getting reflected multiple times. This phenomena is known as multiple reflection of sound. You are familiar with stethoscope, right? Devices like stethoscope and many other musical instruments make use of this multiple reflection of sound. Now let's move on to another phenomena associated with sound wave, that is reverberation. What will happen when you produce sound in an empty room? You can hear a booming sound, isn't it? Do you ever think the reason behind this booming sound? It is due to the persistence of sound due to the multiple reflection. This phenomena is known as reverberation. Next is echo. This term will be familiar for you. What do you mean by an echo? The phenomena of hearing the same sound again after hearing the original sound is known as echo. This is also due to the reflection of sound waves. The minimum distance for the reflecting surface for an echo to be heard is about 17.2 meters. So I think all these are clear for you. So let's wrap up quickly. What all things we studied today? We learned about wave motion first. Then we get to know about mechanical waves and type of mechanical waves, that is transverse wave and longitudinal waves in detail. Then we studied about the characteristics of a wave. What were the characteristics of a wave? Amplitude, wavelength, period, frequency, and speed of a wave. These were the characteristics of a wave. Then we learned about sound waves and the phenomena associated with the sound waves. Reflection of sound, multiple reflection, reverberation, and echo. So I hope all these are clear for you. That's all for today's class. Have a nice day. Thank you.